To solve conservation of momentum problems, we're going to look at the total momentum of everything in the system. As we know, the total momentum of everything in the system doesn't change. It's the same before and it's the same after. So we are going to look in this method at the ideas of before and after. Set them up in two columns, ready for the problem, ready to sort out all the numbers that you have to find the total momentum. Let's take a look at the recoil example and why it is that large firearms are not to be taken lightly. You plan to shoot at a target on the firing range with a bullet the mass of 10 grams at 250 meters per second forward. First thing we do is to set up before and after and ask the ever important question, before what and after what? Set the example in your notes right before and after and think hard about the firing the gun problem. Label them very specifically. You'll be glad you did. It's not wasted pencil. Before what, after what. Pause the video and unpause it when you have work in pencil on your page. Specifically, in this case, it's before the gun is fired and after the gun is fired. Now, in pencil, ready to make any changes necessary, check the momentum of everything before the gun is fired and after the gun is fired. Find the momentum of the bullet, find the momentum of the gun, add them together, everything in the system, to find the total momentum. Write down your answers in pencil, then play the video again once you've got an answer. Ready? Pause. Got an answer? Good. Before the gun is fired, the momentum of the bullet is 0 because it hasn't gone anywhere. Before the gun is fired, the momentum of the rifle is 0. This does not surprise us. Before anything has happened, everything's at rest. The total momentum system is 0. If you are using any of the other numbers in the problem from before, watch out. That was after the gun was fired, not before. So, back to our strategy. Before the event happens, find P1, the momentum of the first object. Find P2, the momentum of the second object. Hey, if there's a third object, find P3 also. Add them all together, find the total momentum. Once you've found the total momentum, then do not press go. Do not collect $200. Do not think. Do not stop. Mindlessly, like an automaton, recopy the total momentum into the after column, character for character, number for number, unit for unit. This is the whole point of the before and after method. The total momentum of the system doesn't change. It stays the same. If you have 0 total momentum before the gun is fired, you're going to have 0 total momentum after the gun is fired. The total means the sum of everything in the system. After the gun is fired, P1, that's the bullet, plus P2 have to add together to make 0. The nice thing about 0 is that you should be able to do a lot of this problem in your head, but let's do it on paper very carefully just to make sure we know how to do it for longer problems. P1, momentum of the bullet. Well, P1 ought to be M1 times V1. Well, there's the mass of the bullet, there's the velocity of the bullet. Carefully, using the numbers given in the problem, find the momentum of the bullet after the gun is fired. Pause the video, press play when you're sure you have your absolutely final answer. Ready? You sure? Did you check your units? And note that the unit of momentogram is kilogram meters per second, not gram meters per second. Make sure you are in the correct units and find your total momentum. This is the part of the problem we can do in our heads if we have a nice number like 0. If the total momentum of the system is 0 because it started at rest and the bullet gets 2.5 kilograms of momentum, how much must the rifle have? Negative 2.5 kilograms? Fantastic. You know that P2 must be negative 2.5 kilograms. If you want to write it down, I certainly won't stop you. If, however, you want to actually do the problem in a way that will enable you to use this method for every single conservation of momentum, anytime, anywhere, ever, take the total, which you have, subtract P1, which you also have, and get your official negative 2.5 kilograms. Now, and only now, you can note that P2 is M2 times V2. P2 is the momentum of the rifle. You can't measure the momentum of the rifle. You can feel it, but you can't see it. What we need here is not the momentum, but the velocity, the speed and the direction. What does negative 2.5 kilograms of momentum look like? Well, we have the mass. We want to know the velocity. So divide out by that 5 kilogram, which is quite heavy for a weapon rifle, and see what you get for V2. If you've got negative 0.5 meters per second, you're in good shape. What does that mean? What is the rifle going to do? Write your final answer in English and indicate that you're done. Pause. Ready? The rifle is going to recoil against your shoulder 0.5 meters per second backward. The before and after method works for all conservation of momentum problems. Decide before what and after what. Find the total momentum of the system, checking in with every object. Recopy that total in the after column. Then look at what happens after the event, see how many objects you have, and distribute that total momentum among them. Last time we had 2 objects. Let's try another problem where we don't have 2 objects. Specifically, the running jump and jumping aboard. Joy, from inside out, comes running up to push the rocket wagon. She is running at 1.5 meters per second forward as she gives a running start and tries to push the wagon as fast as she can. However, the wagon, with Bing Bong aboard, is already moving at 0.5 meters per second. Joy is trying to speed it up, take a running charge, and then she's going to jump onto the wagon too, and the 2 of them will sail off to rescue everybody's psychological well-being. Here's the problem, the running jump. Joy is going to run and jump onto that wagon. Now, set up your before and after columns and answer the important question, before what and after what. Pause for setup, press play when you're ready. We want to find the speed of the wagon after she's jumped aboard. Well, all right then. Before she lands and after she lands. Notice that before she jumps and after she jumps is not quite as useful. After she jumps, she's in the air and the wagon's minding its own business. But after she lands on the wagon, she's adding extra weight. Let's start with before. It's not so bad, we got all the data. Find Joy's momentum. Pause. Find the wagon's momentum. Then add them all up to make the total momentum of the system. Unpause when you're ready to check your work. Ready? Got Joy's momentum? Got the wagon's momentum? No silly typos? Got the total momentum of 75 kilograms? Fantastic. Do not press go. Do not collect $200. Simply recopy the total momentum at the top of the after column. Between Joy and the wagon, they have 75 kilograms of momentum total. Now, what happens after she lands? After Joy lands on the wagon, look. For all practical purposes, there is only one object. There is a wagon with Joy and Bing Bong on it. You can't move the wagon without moving both of them together. And you can't move one of them. You can't move Bing Bong without Bing Bong falling off the wagon and being left behind, poor imaginary pink elephant that he is. We only have one object here. That total momentum doesn't have to be shared. It doesn't have to be divided up. All 75 kilograms will go to that one object. That one object has one mass, and altogether it will move at one speed. It's really funny to call it a total speed. I don't like calling it a total speed, but if we want the labels to match, we can say speed of the total. We can also call it something sensible like V final. Well, that shouldn't be so bad. Find the velocity at which the total wagon and all of its passengers will take off after Joy has given it a running start. Pause, press play to check your work. Ready? Well, the mass of the wagon is now 90 kilograms because it was 60 with just Bing Bong riding, and Joy is an additional 30. That means it should be moving forward at 0.83 or so meters per second. Say what? Only 1 sig fig? All right, 1 sig fig. It's going to be moving forward at about 0.8 meters per second, which is faster than the 0.5 it had originally started with. Why? As Joy gave it an enormous running push and jumped aboard. Notice that although the wagon has significantly sped up, Joy herself has slowed down. Why? Because all of a sudden, instead of just running on her own little cat feet, she's now encumbered with extra weight. This take a running jump and land on a moving vehicle problem is one example of what we're going to call an inelastic collision. Ooh, important new vocabulary word. An inelastic collision is when objects stick together as one. We're going to call this best case scenario a perfectly inelastic collision. One goes bonk, the other goes bonk, and now they're coupled together and move off as one. Take a look at this inelastic collision from your book. We started with 10 m units of momentum plus nothing, and now we have a total mass of 2m, 10m divided by 2m. Beautiful, the m's cancel out. They're going to move off at half speed because they have twice the mass. Look at that nice proportion. Total momentum stays the same. Mass gets doubled, speed gets cut in half. You'll look for the word perfectly in a perfectly inelastic collision to make sure that the two objects are sticking together. This can be done on purpose in the case of two L cars coupling. More often it is not done on purpose, and the fact that there used to be two objects and now there's one wreckage is something that people are seeking to avoid. However, a very, very useful application of an inelastic collision is the idea of landing. If you are running or jumping or flying from anywhere and landing on a moving vehicle, that vehicle and you are now together as one. Set up the generic example for a perfectly inelastic collision in your notes. Use before and after. Before, you have two objects, m1 moving at v1 and m2 moving at v2. Write them with vectors in your notes. I use boldface for vectors in the video, and find the total momentum of the system. Pause and play to check your work. Ready? P1, P2, P total. Immediately after you've written P total, recopy PT into your after column. There it is. That's the total amount of momentum. Do this first. Ready? All done copying? Pause if you need more time. After a perfectly inelastic collision, you have exactly one object. The boat with its new passenger, and of course the driver too. Don't forget about him. It's one mass, total. The total will have one velocity. Now, for every single perfectly inelastic collision anywhere, ever find the total velocity at which the wreckage or the vehicle will move off. Pause. Press play to check your work. Got it? Remember, the total mass is both of them put together. That'll give you the velocity of the total. Pretty nice, huh? Put a box around it. Every time you see a perfectly inelastic collision, you can use this exact setup with any numbers you have. What about an elastic collision? Well, a perfectly elastic collision looks like this, courtesy of pool sharks Joey Schreier, Yoni Shapiro, and Elon Carroll in their physics expo on the physics of pool. A perfectly elastic collision, by definition, is a collision when kinetic energy is also conserved. We will do that more when we do combined momentum and energy problems. The working definition of how to recognize an elastic collision is when the objects bounce back. Set up a generic, perfectly elastic collision for two balls from two different pool sets, M1 and M2, moving at speeds V1 and V2. Do as much as you can before and after. Go! Ready to check? Before, you have P1, you have P2. Add them together, the total is the same afterward. At this stage, know that you need extra information. Somebody has to tell you with an elastic collision either what P1 is doing or what P2 is doing. Use the one you know to find the one you don't know. That's with your momentum, and once you have the momentum and you have the mass, you can find the velocity of whatever happened that you weren't told about, the one part of the elastic collision that you yourself were actually tracking. Between these two, the perfectly inelastic collision and the perfectly elastic collision, you should be in good shape to tackle any collision or interaction.